Welcome to the Explainer. So today we're going to tackle a seriously stubborn illusion. You know the one, where people think being good at math is just about crunching numbers. They picture endless rows of arithmetic, rote memorization, punching keys on calculators. But actually, scratch that. If we peel back the layers, we find something way more fascinating. We're going to dive into the actual frameworks of mathematical reasoning, and honestly, it completely changes how you look at problem solving. Because let's get this straight right off the bat. Math does not just equal calculation. Instead, think of mathematical aptitude as this highly versatile, incredibly dynamic mental toolkit. Rather than just a static set of formulas you memorize, it's actually made up of distinct reasoning styles. These are the literal cognitive tools that scientists, engineers, and, well, logical thinkers use every single day to decode the world. It's really not about the numbers themselves. It's about how we manipulate those numbers to uncover the truth.
Okay, let's dive into this. Here's how we're going to break it down. First, we'll look at foundational tools, then move on to creative connections, tackle the analytical heavy machinery, and finally look at mastering the toolkit.
So, starting off with part one, foundational tools. This is really the classic yin and yang of logic that builds our basic understanding. Now, every logical structure needs a rock-solid base, right? And deductive reasoning is our first pillar here. It begins with general principles like the big, unbreakable rules and applies them to specific cases to ensure absolute certainty. Deduction leaves absolutely zero room for doubt. If your starting premises are true, your conclusion literally has to be true. For example, we know the ironclad rule that all even numbers are divisible by 2. So if we take a specific even number, let's say 28, we deduce with undeniable certainty that 28 is divisible by 2. It's rigid, it's rigorous, and it is perfectly precise.
But wait, what if we don't actually know the rules yet? Well, that brings us to our second foundational tool, inductive reasoning. This is pretty much the exact opposite approach. Instead of starting with the rule, we start with the clues. We move from specific observations to general conclusions. Imagine you're just looking at some numbers and you notice, hey, 2, 4, 6, and 8 are all divisible by 2. From those specific instances, you creatively infer a general rule. Maybe all even numbers are divisible by 2. Induction is incredibly powerful for discovering patterns out in the wild. But, and this is a big but, it's important to see how this contrasts with the certainty of deduction. Inductive conclusions remain probabilistic. It gives us a highly likely theory, for sure, but not an absolute guarantee.
So pitting these two against each other, deduction builds down, from the general to the specific, giving us certainty. Induction, on the other hand, builds up, from the specific to the general, yielding probability. And you know what? You absolutely need both to function at a high level. Induction helps you discover the pattern in the first place, and deduction lets you actually prove it. Which brings us to part two, creative connections. Because honestly, what happens when those foundational tools just aren't enough? Sometimes you hit a wall. When a problem is completely foreign, we rely on analogical reasoning. Think of this as a mental bridge. By comparing similarities between two totally different situations, we can infer brand new insights. When you're stuck, stranded on the side of a problem you just don't get, you build a bridge to something you do understand. And suddenly, let's look at a classic, literally world-changing example of that mental bridge. The idea that an atom is like a solar system. Back in the early days of physics, the structure of the atom was a profound mystery. But scientists used analogical reasoning to compare the tiny invisible atom to the massive, highly visible solar system. By picturing a nucleus as the sun, and electrons spinning around it like planets in orbital motion, boom, an entirely new insight was unlocked. By finding that similarity, they completely illuminated the unknown. Then we have abductive reasoning. If analogical reasoning is a bridge, abductive reasoning is basically the ultimate detective's magnifying glass. You use abduction when you're faced with incomplete information, like when a result in your data seems completely unusual and there's no clear rule to apply. You have to look at the scattered clues and hypothesize the single most likely cause. It's all about finding the best, most plausible explanation for an anomaly. This is the logic behind medical diagnoses, crime scene investigations, and honestly, the leaps you make when you're troubleshooting some weird glitch on your laptop. All right, let's shift gears and move to part 3, analytical heavy machinery. This is where we bring in the big guns designed for predicting, verifying, and dismantling massive problems. First piece of heavy equipment, cause and effect reasoning. This identifies strict relationships between actions and outcomes, and it offers us incredible predictive clarity.
For example, looking at geometry, we know that increasing the radius of a circle directly causes its area to increase proportionally. It's an undeniable chain reaction, right? Action leads to outcome. Mastering this means you don't just know what is happening, you know exactly why it's happening, which allows you to predict future states with amazing accuracy.
Next up is critical thinking. Now, in the context of our mathematical toolkit, critical thinking is the ultimate quality control mechanism. It integrates analysis and evaluation to objectively assess arguments, mathematical proofs, or problem-solving strategies. It's that voice in your head that stops and asks, wait a second, is this proof actually sound? Did I let some bias creep in here? Is there a hidden flaw in this strategy? Because without critical thinking, the other tools can just build a house of cards. But with it, you build a fortress of absolute objectivity. And rounding out our heavy machinery is a true powerhouse, decompositional reasoning. This is the tool that takes an overwhelming large-scale complexity and actually makes it solvable. You know the feeling when you look at a massive system or a terrifyingly long equation and your brain just naturally wants to panic? Well, decompositional reasoning steps in and says, hey, don't look at the whole mountain, just look at the rocks. It systematically breaks complex problems down into much smaller, highly manageable parts. To see this heavy machinery operate, we generally follow 3 steps. Step 1, identify the large, intimidating equation. Step 2, systematically break it down into smaller, isolated parts. And step 3, simplify each part individually, step by step. This perfectly mirrors the concept of taking an impossible problem and just systematically dismantling it until it's just a series of easy, basic tasks. It literally turns the impossible into the inevitable. Finally, we arrive at part 4, mastering the toolkit. Because true genius isn't about having just one tool, it's knowing exactly which one to pull out at the right time. And this brilliantly illustrates our entire mental workshop. True mathematical aptitude is really about synthesis. It's surveying a problem and knowing precisely which specific tool to grab at the exact right moment. Deduction gives us certainty, induction finds the patterns, and analogy builds the bridges. Meanwhile, abduction handles those weird anomalies, cause and effect predicts, critical thinking evaluates, and decomposition manages the insanely complex. Put them all together and they form a complete, basically unstoppable intellectual toolkit. So the crucial takeaway here is this. Math is not just calculation. It's a vast, interconnected web of logical frameworks. And right now, the toolkit is open. The tools are sitting right in front of you, sharpened and ready to go. The only question left is, when you face your next massive problem, your next unexplained anomaly, or your next complex equation, which reasoning will you use next? Keep learning, keep analyzing, and I'll catch you in the next explainer.